Hello, everyone. Welcome here in our session on the Bosch Connectedworld, and here, especially on our ETAS booth. If you're here on site, you can join us and come over and have some nice discussions with me. So today in this session, I would like to give you an overview about software-defined vehicles and especially how we are making the software-defined vehicle a reality. So as you all know, there are big challenges, or not challenges, there's a big change in the automotive industry. And we know these change with the mega trends, personalized, automated, connected, and electrified. So vehicles of tomorrow will fulfill these capabilities. And these trends, they have a common aspect. And this is definitely software. So software will be the differentiating aspect of the vehicles of tomorrow. And as you can read here on this slide, empowering tomorrow's automotive software is our purpose at ETAS. And what do I mean with this? So what is software about? So as you all know, there are two kinds of softwares. The one is there's a software that you as a driver, as a user, you can experience. So you purchase a car because you can have experience with this software, because one vehicle drives differently and behaves differently like the other one. And there's also a different kind of software in the vehicles that is what we call non-differentiating, because as an end user, you will not experience this kind of software. And this is what we always know as base software, middleware, operating system, and stuff like that. And it's for me important to understand that these kind of different softwares are existing, and that in the end, as an end user, you will do your purchase decision on the software that is really making the difference. And we as ETAS, we want the limited numbers of developers, of software developers, to focus on the software that makes the difference. And this is key for us. And in this session, I want to show you about what we understand as software-defined vehicle and how we support in speeding up the evolution to a software-defined vehicle. And of course, we do not start tomorrow like it's written here, we start today. So software-defined vehicle, what is it about? As you can see here, it's important that we have a vehicle where you continuously add value over a lifetime. So even if the car gets 1, 2, 3 years old, you will be continuously getting updates and new features and new experience with this car. And it's important to bring the developer here in this loop and very close to the vehicle. You can see it here. So the developer is key in this picture, and it's part of the development shown here, and it's very important to have flexible data access to the vehicle. So whenever the developer wants to get data, he should be enabled to get data, and specifically the data he's interested in. And the second part is you need to be efficient in over-the-air updates. So whenever you have a new feature, you should be very efficient in bringing this feature into the vehicle. But how do we measure if we are on the right way to a software-defined vehicle? How can we measure it? How can we see if we are good or if you are bad? And here you can see we just take some measures that are well known in the IT industry, and it's a measuring of software delivery capabilities. And here you can see 3 examples of how you can measure how successful you are in software delivery. So let me first start with the first one. So it's about deployment frequency. So deployment frequency, it's how often you can deploy new software in a given time frame. And of course, we want to get from a low performance, and you can see if we're able to deploy new software within months to a very short time, and here in the end to doing softwares on demand. So we want to become elite. And there's an interesting aspect in deployment frequency because it also has some organizational findings. So there's a finding, if you see these organizations that are able to deliver with high frequency, very short, small iterations of new software, you will see that this kind of organization is able to scale, because if you add new developers to this kind of organization, you will see that the output for each developer that you add will be very high. And the opposite, if you have organizations that are very slow in software deployment and ship very big packages of software, if you add new developers to this kind of organization, you will see that the output is quite low. That's an interesting finding, and it gives you information about how are you able to scale. Lead time for change. This is the measure time from a commit until you get it to production. And this metric, of course, correlates with the speed of your development team, but also with the quality of your development team. And there's also a big difference in thinking of developing in a smartphone world, for instance, because in the vehicle, once you add the software, the cloud to the vehicle, and you open your system for third-party software, you open a huge corridor or a huge environment for development complexity, because in the end you have to ensure safety and security. Mean time to repair. This is the time that is needed to, once you find a quality issue, until your organization is able to solve this issue and you fix the issue in your vehicle. So we want to get from, let's say, low performer here to elite, and want to really be efficient in software delivery. Why do we want to achieve this? Because there's a clear rationale behind that, because we see that being very good and efficient in software delivery leads to being very successful in business. And you can see it on this slide. It says that high performers have 50% higher market capitalization growth compared to low performers, and high performers are twice as likely to exceed organizational performance goals. And this is profitability, productivity, market share, and number of customers. So you see, all of us want to be, of course, successful in business, and that's why we have to increase our software delivery capabilities. Here I would like to give you some other examples why we want to achieve this fully programmable vehicle, or the software-defined vehicle, because it will help us in increasing software delivery to the vehicle, so we can improve the innovation force that we have in our vehicles. We can easily bring new innovations into our vehicles. We are able to bring in new services to your vehicles by adding the cloud. And this comes also with new business models. So for instance, you can buy a feature just for a specific time frame. We have improved lifecycle management, because you, at any point in time, you know about your vehicles, where they're located, which kind of software configuration is deployed, and which one has to be updated, for instance. You will be able to do really user-centric and user-oriented development by just collecting the necessary data, bringing in new features, new functions, and really learning from the behavior of users, of drivers, if they like it, if they don't like it. You have a kind of interaction with your drivers, and you will really fast in learning and adapting and bringing new value to your customers. That in the end will be paid, of course. Enhanced security, we will be able to be up to date to security solutions, because we can update, of course. And some other examples like lower quality costs, because you don't have to get your vehicles back to the garage to make updates. Software scalability, because you can take over software from the first version of a vehicle to the next version of the vehicle, like you know it in the smartphone area. And of course, bringing new software and new valuable software to your vehicles will also increase your customer loyalty, because you create an ecosystem where the customer feels very good in, and he will not be so easily changed from one brand to the other brand. So it's very interesting to reach a fully programmable vehicle. But the question is, why can't we just build up a fully programmable vehicle or a software-defined vehicle? Yeah, because in the automotive industry, we have to deal with some legacy. So we cannot start from scratch. We have established way of working that we used the last decades. And now we want to introduce a new kind of working model. And this is what we call DevOps. Because DevOps is what we know is very successful, or the most successful way of bringing in new software incrementally into the systems. But we cannot just switch from what we're used to do, and we develop currently by using a V-model approach, where you really have some specification, implementation, and verification, and then you ship it to the vehicles. But we want to go to this continuously loop where we measure, where we learn, where we bring a new software, we build it, we test it, we integrate it, and we operate it and close the loop again. And the ultimate goal is to have this DevOps loop in a very fast iterations. So accelerate this DevOps loop is key. We will see it on the next slide. Important to know is also that we will still see different kind of working methodologies in the vehicle, because there are different kind of systems available in a vehicle where you need different kind of tooling and different kind of approaches to efficiently develop software. This is especially for the case, you can see it on the slide, for embedded, which is basically software that is safety critical, so like braking systems or battery management. We will have a different kind of working methodology for ADAS AD, so advanced driver assistance systems, and automated driving, where you use different tools, different kind of learning, different kind of AI, for instance, and different kind of deployment. And we have here the third example, vehicle edge. This is what is very similar to what we know from smartphones, where we have a lot of dynamic in terms of bringing new apps in, deleting apps, and combination of apps. So this is what we call vehicle edge. And to visualize this issue, what we face today, so this is where we are today, we know that DevOps is very efficient and a good way of working, and we know this from back-end development. So working in a cloud and back-end systems, here we know we have very high capability achievement of software delivery, because we already use agile development frameworks, we use DevOps, we have continuous integration, we have infinite number of hardware, basically we can scale, and we use container technology. This makes this way of working in the cloud and the back-end side very efficient. So why not just taking over this approach and bring it to the vehicle? Should be the same approach, right? But the real world shows us that we are not there right now. So we are very slow. We are very slow on the vehicle side. And this is because we are limited in hardware. So we need to test software on a dedicated hardware device. We have to deal with real-time capabilities. We need to do a homologation. And as said, we are working with a V-model approach. So this issue is shown here. So it leads to the fact that we are very slow in software delivery. Here it shows more than 1 month. It can also take up to half a year or a year. And it will slow us down. So what can we now do to accelerate and to be better, to become better in software delivery capabilities? It's clear, we need to speed up the left-hand side of this chart. So we need to speed up the automotive part. And how can we do this? We can already do this today by introducing virtualization. So we can test completely virtual in a virtual world. We can already use containerization in order to run efficiently applications, vehicle applications. And we can use cloud-based tool chains to automate, to collaborate, and to work very efficiently together in a common space. And the fourth point here is we can abstract hardware from software by introducing of middleware technologies. So what does it concrete mean? What can we now do today. Because we need to evolve from where we are now, very slow, to very fast by doing things now. So we don't want to wait. We recommend to do the following. You could already establish tool chains that are automotive grade, so that can be used to develop automotive grade software, and introduce continuous X pipelines. We can also establish a collaboration platform where developers from different companies and departments, of course, but also cross-company can work together. We can already introduce container technology to run efficiently vehicle apps, but important for the vehicle side, we need to ensure safety. So whenever a vehicle app interacts with a safety relevant system, we need to take care for this kind of thing. Then we can abstract hardware from software and the underlying software layers. We can introduce complete virtual verification and validation, and this on vehicle level, so you can scale your simulations in the cloud and run multiple massively parallelized tests in the cloud. You can enable flexible data acquisition and processing in the vehicle. And you can already, or you should let the cloud become a major part of your system. Not only an extension, but really a major part. So the software-defined vehicle belongs to the software. The cloud belongs to the software-defined vehicle. It's a part of the software-defined vehicle. And reduce integration effort. You can also reduce the integration effort by setting up the right systems. And you should introduce holistic cybersecurity to be in your whole DevOps cycle. All right, but this sounds now a little bit abstract, right? So let's dig into deeper and give a concrete example on how that looks like. So I would like to give you an example about the following. How could a software development toolchain look like that enables continuous X and automation? How can people and developer work together in a collaborative way? And how can we do virtual validation and verification? I just want to show it how it could look like and how the world is today. So how does a software developer today work? So there you can see the software developer, and he gets a task from a project manager. And the project manager wants to have some new code, some new feature, for instance. The software developer, of course, is motivated and wants to start coding. He really wants to develop this software. And this is his task, right? But now there comes the truth. He cannot just start coding because, dependent on the project in which he's working in, he needs to set up the right tool chain. And this tool chain is a very complex ecosystem where a lot of tools have to interact with each other. You need the right versions, you need the right conversion of data. And here you can see this poor guy has a lot of tasks to do, which is anything but not software development. So of course, the project manager here gets nervous because he does not get his software in time. And the software developer here is, of course, also very disappointed because he was not able to do the fun part of his work, right? And how does it look like in a project, in a bigger project? Because there's not only one developer, but there are multiple developers, and they are sitting in different departments and different organizations. And so you can see by this color coding here that these tool chains are also different, and so they are not compatible to each other. So a typical way of working is you contribute your code, your development, to a bigger system, and in this time you have to wait, right? So you deliver your software, but it's not tested because you don't have the capability to test your software. And in this time, you just have to wait until the last developer here in this chain delivered his code. In the end, everything is available and you can do the integration test. And as you can see here already, the test failed. But what information do now the developers get back? They just get the information, everything failed. But they don't know who is responsible for this error. As you can see here, these two guys, they had the right software delivered, and it fits to the whole system, but they cannot see it because they just get back the information it's failed. So what we say is software developer lose major time of their available time, which is of course limited, for administrative tasks, waiting for test results and analysis of non-transparent test results. So now, how could a good word look like? Because we want to speed that up, right? So we want to have an automated, a virtual, and a collaborative way of working. So our approach is here, bringing all these tool chains together in one tool chain that can be used by all the developers. The same tool chain. It's in the cloud, so you can exchange data, you can communicate, you can collaborate. The integration test is part of this tool chain, and it's accessible at any point in time. So the software developer can work in parallel. Nobody has to wait. Whenever you have a software delivery and it fails, you get this feedback immediately back, and you're able to just update your code, integrate it again, test it, and you're done. So you can speed up and you can really use the time efficiently of your developers. And this leads to the result that these software packages can be shipped very efficiently. And the basic idea is, of course, having more time, you can contribute with more software, and this approach is continuously, and you will be able to ship in very short frequencies, or in a high frequency, you can ship software to the vehicles. So the life of this developer will be better because the same tasks he wants to contribute with software, he wants to start coding. In the new world, he can just access his development environment and he can start coding, testing, and delivering a software package where he knows that this is working. All right, so this was the dev part, the development part, how this could look like. And now we are coming to the ops part, so the operational part. But it's important to say that the development part is also important for the operational part, because now I will give you an example of over-the-air updates, how over-the-air updates in future could look like. But it's important that you cannot only optimize a process here, because over-the-air updates in a new generation will also need the corresponding tooling on the development part. So how does over-the-air update look like today? Let's say we have a quality issue in our field, indicated here by this red car. One of the ECUs, one of the components, has a bug. So now we want to update this particular vehicle. But not only this particular vehicle, we need to find out which of all the other vehicles in the fleet could be affected by this software. So now the tedious task begins, because this fleet manager here, he has to go through a lot of databases and try to find the right connections here and to the right dependencies, and really have to go manual through all of these lists in order to find the right vehicles that are affected by this software issue. So this again takes a lot of time and is quite frustrating work to do. And in the end, you found the right vehicles that need to be updated. But since they are very different in configuration, still in software configuration, you need to ensure that your software update is really successful. Even if you only have a small piece in your software package that needs to be updated, you will update the full stack here in order to be on the safe side and have a working vehicle in the end. So this again takes a lot of time, not time from the developer, but time from the car owner, because he has to really wait for this update. And this currently takes up in the market up to 7 hours, where a customer cannot use his car. Okay, this is also very frustrating for the car driver, of course. Okay, so what is now our approach of OTA? And we call this OTA Next Generation. The idea here is that we don't only want to do software updates by quality issues. We don't mainly want to do updates because we have new software, because a lot of software developers contributing continuously with new software. This is indicated by this app store. So imagine there's a software developer and he contributes with a new version of his software. This is a perfectly keyless app that we push into the cloud and is available as a software. And now, since the development tooling, this is why the development part is very important, contributes with the right information to the cloud, so that the cloud is now able to know about which kind of vehicles are affected. So which user had ordered, for instance, this kind of vehicle app. So it will just take some time to scan the vehicles, and in the end, we know, okay, these 3 vehicles in this example are affected by this software update. So what happens now is that we calculate a so-called new desired state. So the cloud calculates, based on the new software information, a new desired state for the vehicle. It's some kind of blueprint that is created, and this blueprint is transferred to the vehicle. So the vehicle gets information of the new plan here, and there's a lot of logic now in the vehicle side, on the vehicle side. So because the vehicle can now see what is his current state of software and what is the desired state he wants to reach. And so it can compare and it can check which kind of software building blocks are missing. And by knowing this, only these particular building blocks here can now be downloaded from the cloud. So it's not a push from the cloud, but it's a pull from the vehicles. And this makes the whole process more efficient. And this desired state is calculated for all the vehicles because they will be different. And the vehicles will only download the particular software elements that are needed. Okay, so this was an example for OTA Next Gen. And as you can see in both examples, there are a lot of changes in this world. We are in the middle of a revolution to the software-defined vehicle. And we believe in this revolution, the highest customer satisfaction, which is clearly our goal, can be achieved if we achieve the capability to have systems compatible. So bringing apps together, systems together, combining things will increase the customer value in the end. And compatibility can be achieved by standardization. And standardization is what we also know from automotive, for sure. But we as ETAS, we believe that we should go a different approach, what we know as best practice from the IT industry. So standardization means having the same APIs and in the end speaking the same language between systems. And following the IT industry as a best practice, we go for open source. So, and this is where we want to recommend you or ask you to join also our initiative, because we don't want to make a decision between make and buy, but we want to follow a third operation and this option, and this is integrate and collaborate. And with this, I will finish my presentation. And as said, there are a lot of activities in the open source, like Eclipse, Software Defined Vehicle Working Group, SOAFI, Covesa, and we would ask you to join our automotive revolution and do this revolution together. Thank you very much.